Hello guys, today we're going to start talking about gravity. So last class we were talking about Newton's third law, which is the force pair. So every action has an equal but opposite reaction. Hopefully you guys were able to get through that lab okay. I had recorded the data and inserted those images of the graphs for you. So you guys could have experienced the exact same lab that we did in class. So if you just read through that and kind of figured out what was going on at each step, and then you had the graph in there for you. So today we're going to start talking about gravity. We're going to talk about the four fundamental forces that govern the universe, the different gravitational forces of objects, how that's different from acceleration, like the gravity of acceleration that we've been using, and then weight versus mass and different situations that might apply. So we have four fundamental forces that govern our entire universe. Okay, so if these four forces are altered in any way at all, it would literally change the structure of the entire universe. So the first one's going to be your strong nuclear force. These are the strongest forces. They only act on a very short range, though. So we're talking the space between subatomic particles. So they are going to hold the nuclei of the atoms together. Okay, so that is what's keeping your protons and neutrons together within the center of an atom. And we all know that if you split an atom apart, you get an enormous release of energy. So that would be what you are doing if you are breaking that apart. You'd be breaking the strong nuclear force. The next fundamental force is electromagnetic force. So these are the second strongest forces. These can be longer ranged, they can be attractive or repulsive, and they're only going to act between pieces of matter with electrical charge. So this is something like a magnet or some charged metals or something like that. So these are also very strong forces, and we see this if you've ever taken magnets and put them together. Obviously, they will be attracted to one another, but if you flip one side of it, they'll also be repelled from one another with an equal amount of force. So electromagnetic force is second strongest, can work at longer ranges, which we obviously know because there's a magnetic field on the Earth, okay, so it's pretty large there. The last two, I should say, of our fundamental forces is going to be the weak nuclear force. So this is the second weakest force. So it has a very short range, and this is what's responsible for radioactive decay and neutrino interaction. So here's an example of radioactive decay of an atom. It really just means that you are losing some particles here, and it's giving off energy in the form of radiation. So it's not a very strong force, only works at a pretty short range. And then the one we're going to focus on today is gravitational force. So this is by far the weakest force, but it's very, very long range. So this is evidence in the setup of the structure of the universe, okay? So we know that a gravitational force, is keeping all of our planets in orbit, right? So that's a very long distance.
Hey, can I ask you something?
Oh, okay. Miss Farah just popped in, so I have no idea what I was talking about. I'm just going to start over. So here we've got, what were we talking about? Gravitational force, okay? So again, super, super long range. This is obviously what keeps our planets in orbit. It's always going to be attractive. It's never repulsive. And it's going to act between any two pieces of matter in the universe. So any two pieces of matter, it doesn't matter if it's a planet or if it's a speck of dust, everything has a gravitational force. So that's what we're going to focus on today. Okay, so since we're focusing on Newtonian mechanics as opposed to quantum mechanics, we're going to just be talking about gravitational force today, and it's a whole topic within itself. So gravity is going to be your attractive force, which means that it's always pulling objects closer to it. So it's also a distance force, like a long-range force, meaning that objects don't have to be touching. They don't even need to be near each other to experience that pull. So this is the classic, Newton getting the apple falling on his head example. So, the story goes that he was sitting under the apple tree and an apple fell and hit him on the head, and he discovered gravity, or came up with an idea that something had to exist that was pulling this apple, it was pulling objects back down to the earth. So we know that gravity is going to act between any mass. So all masses of any objects or particles or atoms or anything. So this is a theory on how like our sun and planets and stars were created. The theory is that there were just these tiny bits of cosmic dust in existing in the universe, and they were attracted to one another because they all have their own gravitational fields, and they began like kind of combining into these slightly larger like conglomerations of things. So you kind of got these like cosmic dust bunnies kind of floating around, and then they are larger, right? So if you put a bunch of smaller pieces together, you get a larger piece. So then all of those larger pieces, those little dust bunnies, started to attract more dust bunnies, and they just kept getting bigger and bigger and bigger. So eventually these created stars, planets, and moons. So if that's true, why can't we feel the gravitational pull between us and anything around us, right? Because technically speaking, like I have a gravitational pull to my computer has a gravitational pull on me, but we don't feel that, right? You don't feel the gravitational pull between you and your phone, although it may feel that way sometimes. So the gravitational force is going to be negligible compared to the force between yourself and the Earth. So even though it does exist, it's going to be very, very, very small. And since the force of the Earth, the gravitational force of the Earth is quite large, it's kind of like trumping any other small gravitational fields that we have going on elsewhere. So in theory, if you and your one true love are the only two things left in the whole universe, let's say you're billions of kilometers apart, would you ever meet? And the answer to that is yes. It could take a very long time, but you would be attracted to one another through gravity. So you would eventually, neither of you would probably survive that, but eventually you would come back together because you're attracted to one another literally. So here is kind of an example of how the distance and the mass can affect that. So if the mass increases, the force of gravity increases. So mass is it's proportional to the force of gravity, and the distance is going to be inversely proportional to gravity. Okay, so if the distance increases, the force of gravity will be smaller. As they get closer, the force of gravity gets larger. And then if your mass suddenly doubles or triples, then the gravity would also get larger there. So if we're going to apply gravity to some analysis questions here, remember, we know that mass is measured in kilograms and weight is measured in newtons. Pounds would be the non-metric unit for that. So we know that we have kilograms to describe mass, or grams, and then weight should be in newtons. So weight will be affected by gravity and mass will not, which makes sense, right? So if let's say that you are 70 kilograms and you have a weight of 150 pounds, and then you launched yourself out to the moon, you would still have a mass of 70 kilograms, but your weight would be different, right? Because the gravity on the moon is much less. So you would weigh much less. So knowing what we know that the net force is equal to mass times acceleration. If gravity is the only force acting on the object, the acceleration is going to be equal to the gravity for that situation. So if we're talking about on Earth, we know the gravity on Earth is 9.8. So therefore, the force of gravity, so the net force is different than the force of gravity, right? Gravity itself is different than the force of gravity. The force of gravity is how the gravity is affecting the force being pulled on you. So force of gravity will be measured in newtons, where gravity is in meters per second squared. So knowing that this is our formula for net force, if gravity is acting on the object, we're going to consider A as G. So therefore, the force of gravity is going to be equal to the mass times gravity. And on Earth, like I just said, we know that that is 9.8 meters per second squared down, or negative 9.8. So in this example, we have a 150-gram apple experiencing gravity, and it falls towards the Earth. Determine the force of gravity acting on the apple. So the force of gravity is going to be the mass times gravity. Okay, so we know the mass of the apple is 150 grams. We know that mass is measured in kilograms, so we need to convert this 150 grams into kilograms. And then we know that gravity is 9.8. So we're going to substitute those values into this formula. So we have the force of gravity is equal to 0.15 times negative 9.8, which would give you this little menu on the bottom, just likes to hang out there. The force of gravity is going to be negative 1.47 newtons. So the way that you would write this out to be correct would be the force of gravity on the apple is 1.5 newtons down. So you'll notice that you get that it says D and it's in brackets at the end there. That's your directional notation. So you're going to have, these are all magnitudes, so they're going to have the value, the unit, and the direction on them always. So you always have to describe what direction it's being applied or what direction the object's moving. So with terminal velocity during free fall, an object does not necessarily accelerate downward the entire time. So if air resistance is great enough, it's going to balance the force of gravity. So if an object has a balanced amount of air resistance, like going upwards versus its force of gravity falling downward, it's going to fall at a constant velocity. And that's referred to as terminal velocity. It means the object will not fall with any greater velocity than what it's currently falling at. So in this example, we're going to determine the acceleration of a 65 kilogram skydiver who, he first is going to jump out of the plane and experience 115 newtons of air resistance, and then B, what are those values when he achieves terminal velocity? So if you look at the example on the left, I don't want to point out it here because that little menu is going to pop up and it'll erase or cover up some of the stuff on the screen. So if you look at the example on the left, we have our free body diagram. Always have to draw a free body diagram with these. So you have the box and then the force vector arrows coming off of that. So air resistance is going upward. We know it's only 115 newtons. And then we have the force of gravity coming down. So it doesn't tell us what the force of gravity is, but we know we can calculate that. So if we have F of G is equal to mg, so the force of gravity is equal to mass times gravity. So we'll just substitute in the values that we know. So the force of gravity is equal to 65 times 9.8, which I guess technically would be negative 9.8. So in your force of gravity, we know it's already going downward. So it's 637 newtons down. If we were going to find the acceleration, which is what it really is asking for here, you would use your acceleration formula. This is just your net force formula rearranged. So we have acceleration equal to the net force divided by the mass. So our net force in this case is going to be the 637 down minus the 115 newtons up to get the difference there. So the net force is 522 divided by the mass of 65, which gives us an acceleration at this point in time at 8.03 meters per second squared. So that being said, like ideally, if we're talking about being on Earth, we know the acceleration should be somewhere around 9.8. So here with 8.03, that's in the ballpark. It's obviously not exact, but this is just an example question so there's a good chance that some of these numbers are a little bit off. So maybe at this moment in time, they were only accelerating at 8.03 meters per second, and it was increasing still. So on the right-hand side, you are doing like letter B here. So what's happening when it's achieving terminal velocity? So this free body diagram is representing an equal balance of air resistance versus the force of gravity. So we know that terminal velocity is when the net force is 0. So that means that if our force of gravity is 637 newtons down, then the force of air resistance has to be equal to 637 newtons up. It has to balance it out. So the last section of this is talking about your gravitational force, kind of on a larger scale. So we already discussed that gravitational force depends on the masses and the distance of each object. So this is represented mathematically with Newton's law of universal gravitation. So the gravitational force of a sphere is going to be the same whether you're looking at the entire sphere or just the center. So when you are measuring the distances, you are looking at it from the center of the objects. Okay, so no matter what object it is, if it's two people standing next to each other, you're looking at the center of that person compared to the center of the other person. So if you think about it this way, like if you have a gravitational force, like a force field around you, it's going to go out in all directions, right? So you're getting the the radius of your gravitational force, and comparing that to the radius, the gravitational force of the other object. So what we're looking at here is this formula on the left-hand side. So the force of gravity is going to be equal to an uppercase G, which is the constant used for universal gravitation, which is on the right side. It's telling you right here, it's 6.673 times 10 to the negative 11th, and it has its own special unit. So it's Newton meters squared divided by kilograms squared. So that's the value you would sub in for G, the capital G. And then you have mass 1 times mass 2 divided by the radius, or the distance between the centers of the two objects squared. So this on the right-hand side is just kind of breaking that down for you. So if you had a question, it would look something like this. This is a pretty simple example, but it's the same formula. And as we know, we can always use this formula to solve for one of the other variables. So be looking out for that too. You could use this to solve for the distance between them or the mass of one of the objects, depending on what information you are given. So this is our last example. How attracted are two members of our class to one another? So if we assume person 1 is 65 kilograms and person 2 is 85 kilograms, and they're 1.5 meters apart, okay? So we have the mass of both of the people. We have the distance, which is that R. We know that the capital G is the constant. So we're just subbing all this in and then solving for the force of gravity. So here, that's exactly what we did on the right-hand side. So the universal gravitational constant is 6.67 times 10 to the negative 11 times the mass of the first person, which is 65, times the other mass of 85. All of that is divided by 1.5 squared. So when you solve this, you're going to get the force of gravity between these two people to be 1.63 times 10 to the negative 7th newtons. So to write this out correctly, to give the complete answer, you would have to have the direction, the unit, and the value. So this answer would address all of that. So you could say that both classmates are attracted to each other. That's your direction. They're attracted to each other equally with a force of 1.6 times 10 to the negative 7th newtons. Another way you could write that is you could say they are attracted with a force of 1.6 times 10 to the negative 7th newtons, and then in brackets you could say towards one another. That's just another way to say it. But either way, just make sure that with these answers, these are all going to be vector measurements. So you're going to have the value, the unit, and the direction. And that's it for today. So I feel like I went through that pretty quick, but I've got some people coming in here in a few minutes. So please let me know if you have any questions. Obviously, you could go back and rewatch parts of this video if you need to. And then you guys have a virtual lab sort of here to do. So we have 2 things to do today for an assignment. You're going to have practice problems like we always do, and then you will have the lab. So the lab that I'm giving you is the terminal velocity lab that we're completing in class, but I am providing the data for you. So you're just analyzing the data. Honestly, it's probably a little less work than what you'd be doing if you were in class, but it gives you kind of the same, at least the same analysis piece for that. So please give these a shot. Let me know if you have any questions. Please let me know if you want to set up a Zoom or anything like that. I am happy to do that. So I will talk to you guys next time.